All right, my friends, we've got the Audioquest Thunderbird Zero speaker cable with 72-volt dielectric bias system. Is this legit science or is it snake oil? That's the question we're going to be answering in today's video. All right, my friends, I've waited decades to get my hands on some Audioquest speaker cables or any kind of cable that they make just to check them out. This series, the Thunderbird series, has what they call the dielectric biasing system. And you can see when you press the little LED light, it lights up. There's basically 72-volt bias. There's 6 12-volt batteries in series here. They do this on a bunch of their high-end speaker cables, interconnects, and I think even their power cords. And their claim on why they do this is they want to eliminate distortions that occur in the dielectric. Now, I know I often talk about snake oil and cables, and I'm not trying to single out Audioquest, but let's be honest, they are the biggest cable maker of high-end cables right now. And they also make a lot of claims on their website that go against basic and understood engineering principles. We're talking about established science in cables and signal transmission, stuff that's been around for, hundreds of years, that's very well understood. Audioquest claims they have their own understanding that can't be evaluated with traditional means. So I'm going to try to do that as best as I can, and we're going to go over some of their claims. So they've made a lot of claims about how there's so many different distortions in cables and how they have to impedance match. Now, I want to give you a little bit background in case you guys don't know. Before I did Audioholics full-time, I got my electrical engineer degree. I took graduate courses in microwave engineering, and I spent 6 to 7 years designing small signal-based equipment that would run over POTS. So I did ADSL, MVL, all these different phone technologies that also ran high-speed data. And I spent a lot of time worrying about transmission line effects. I was transmitting very small signals down a phone line, for miles, and impedance matching made a lot of sense in those cases because we were transmitting, 7 megabit data, very high frequency stuff over phone lines. You have to be really understanding about how the importance of signal integrity, low noise, low distortion, proper impedance matching. I also did work in government defense, and I did audio communication systems. So a lot of stuff where I had to do board layouts. I understand transmission line behavior. And the bottom line when it comes to transmission lines is it's not an issue at audio frequencies with speaker cables. And we're going to go into that. I've got several articles I'm going to reference if you guys want to read ahead. But let's get down to the nitty-gritty on this speaker cable. Now, before we even go into the measurements, because I'm going to show you the measurements on these cables, I just want to point out the fact that this is a really thick cable. It's very stiff. This is a very difficult cable to put in a rack. It's very difficult to connect to your speakers because it puts, especially your amplifiers, it puts a lot of tension on them. In fact, when I was connecting one of these cables to one of my speakers, to my amplifier, I had to push it in, and then as soon as when I pushed it in, it locked down and then it broke. So these are $5,000 speaker cables, and the banana connector broke on it. I've never, in 20 plus years, I've never broken a banana plug. So I was shocked to see this. And if you look inside the barrel of this connector, it's hollow, but it has like a center pin. I don't know if it's supposed to be silver. It kind of looks like copper-clad aluminum. I can't really tell. But the bottom line is these are very brittle connectors. So if you do have these cables or you're considering buying these cables, keep that in mind because these could break pretty easily. You don't want to break a $5,000 pair of cables. That's right. These cables are $5,000 for an 8-foot pair. The most expensive cables I've ever brought in to measure. So I want to show you guys, as you know, I have an impedance analyzer, the Wayne Kerr, and it's the 4300 model. I do all my LCR measurements on cables. And why do I do LCR measurements? Basically, it's very understood what a cable is. And if you can measure the 3 parameters of a cable, you know its behavior. Those parameters include resistance, inductance, and capacitance. I can measure all that stuff on this impedance analyzer. And that's what I want to show you right now. So the first thing I want to show you is the gauge of the cable. Audioquest claims it's a 10 gauge cable. Now, if you look at my measurement here, I just kind of took the DC resistance, the loop resistance, and I plotted it on a curve of gauge. Now, I got 11 gauge, and the reason why I got 11 gauge is because I could not take these connectors off. And there's some contact resistance, and because this is only an 8-foot length, it creates a little bit error in the DC resistance because of the contact. So that's adding to the resistance. I'm going to give them a pass that this is a 10 gauge cable. I'm not going to say it's an 11 gauge cable. I'm going to tell them, I agree, it's a 10 gauge cable. So the first thing I want to look at, and one of Audioquest's biggest claim, is that their cables solve skin effect, that there's no skin effect in their cables. What skin effect is, and I have an article I want to show you as a quick reference so you guys can understand this. And I've written these articles, you know, decades ago. So this stuff has like been around for quite some time. And I want to show you here. And I'm going to put a link in the description below. So here I did an article on skin effect relevance in speaker cables. And what happens is as the frequencies go up in a cable, the current density flows towards the surface. What's called, what you have here is a skin depth, and it's a frequency dependent resistance. And I have all the equations here for you propeller heads that want to go through this. I did all this work, you know, back in 2003, 2004, and I did all the calculations here. This is the equation for figuring out the skin depth. It's a number divided by the frequency. And then here's the ratio. And then I plotted it out for 12 gauge cable. And as you can see, as frequency goes up, the ratio of AC resistance divided by DC resistance goes up, which means you have more AC resistance than you do at DC resistance. So at very low frequencies, your RAC is equal about to your RDC. As you go up in frequency, and I'm talking past 20 kilohertz, I'm talking hundreds of kilohertz, you get more AC resistance, which means less current could go through the cable, and most of the current goes on the surface of the conductors. And as a result, it reduces your internal inductance, and you can see the series reductance of the cable go down, and we'll go over that in a little bit. So when I simulated the AC resistance of a 12 gauge cable, I showed in measurements that in calculations, you get a 34% increase of 12 gauge cable resistance at 20K. But here's the interesting thing. These equations all assume solid core conductors. Most 12 gauge cable are stranded, and they have if you have a high strand count cable, your AC resistance is actually much less, because what happens there is when you have multi-stranded cable, there's a little bit of an air gap between the strands, and that acts as almost like an insulator. So it almost behaves like a Litz cable, which means your AC resistance goes down because each of the individual conductors act as their own path for current. So you can see the actual measurement of a 12 gauge cable at 20 kilohertz only increases the resistance from skin effect only 3%. So it's very negligible. And this is why I've always been a much bigger fan of stranded cable over solid core cable. 2 reasons. Stranded cable is more flexible, and the second reason is because of the AC resistance profile is typically better on a stranded cable versus an equivalent solid core conductor cable. And Audioquest is all about solid conductors. They claim that the strands of a cable cause strand jumping, which causes diode rectification, which causes distortion. Now that's impossible because cable is a linear device. It can't introduce a nonlinear distortion. If that was true, we would never be able to propagate signals for miles like we did with the telecom stuff or anything. You wouldn't be able to transmit any data if the cable itself was causing distortions. Now, we could talk about impedance mismatches and all that other stuff, but that's separate from what I'm talking about, nonlinear distortions. Cables can't do that. It's physically impossible for a cable to cause a nonlinear distortion. So I want to show you the AC resistance of this Thunderbird. So here's a very interesting graph. I basically took 10 gauge cable, which I consider the gold standard for speaker cables, which is the blue. And I took the Kimber ATC, which is an expensive cable. You guys know it's my reference cable. I always talk good about Kimber because I just like their cable. It measures better than 10 gauge. And then I took the Thunderbird from Audioquest, which is this light green. I probably should have chosen a different color. I apologize for that. But as you see, as frequency goes up, the resistance, the RS, goes up as well. Now look at it for the 10 gauge cable. And you can see it's down here. It's down a little bit above 2 ohms. And then when you get to 20 kilohertz, there's a slight increase to, a little under 3, I'm sorry, milliohms, not ohms. This is milliohms per foot loop resistance. Look at the Audioquest cable. Look at the slope of the AC resistance. This cable has the worst problem with skin effect, not the best. The cable that they've claimed for decades that solves skin effect actually has more AC resistance versus frequency than standard 10 gauge cable from Belden. And look at the Kimber in respect to that. The Kimber is actually the flattest AC resistance out of all the cables. Kimber doesn't even make claims on their website that they solve skin effect, but in fact, because they're using multiple strands in a braided configuration, this cable is superior. The Kimber cable has much less problems with skin effect. Not that any of these cables are even a problem at audio frequency skin effect. This is just, I'm showing you the measurements. This does not necessarily translate to anything that's audible. I'm just showing you the science here. The company that's claiming that they've solved skin effect obviously has not solved skin effect because their cable is skinning at audio frequencies. As you can see, the AC resistance go up. Now, as I told you before, as you see AC resistance go up, because the current density flows more on the outer conductors, your internal inductance goes down, and you should see the inductance drop as frequency increases. And that's what we have here. If you see, we have the blue is the 10 gauge zip cord. You can see it a little bit above almost 20 kilohertz. I'm going to say around 15 kilohertz. You start seeing the internal inductance go down to the cable because of the skinning of the 10 gauge. The Kimber cable is almost like a straight line. It's perfect. I mean, all the way out to 100. This is 100 kilohertz. So this is well beyond human hearing. Human hearing stops, if you're lucky, at 20K. And as you get older, it goes down. Now, again, we see here the inductance of the Audioquest cable is dropping from internal inductance from skin effect. Now, here's another interesting thing. Look how much higher the inductance is of this expensive Audioquest cable. This inductance is over 0.2 microhenries per foot. That's about what I measure on very cheap 14 gauge zip cord you get at Home Depot. I was actually expecting the Audioquest to have low inductance like the Kimber. You can see the Kimber is below 0.05 microhenries per foot. The Kimber is the lowest inductance cable that I've measured in recent time. And then the 10 gauge is like 0.16 microhenries per foot. So the actual 10 gauge Belden cable has lower inductance. And I want to show you, if you guys want to figure out how much inductance a cable has, I'm going to show you a little trick here that you can look at. If I can figure out how to get the screen off. Okay. So if you go to Audioquest's literature here, if you want to minimize cable inductance, you really want your plus and your minus conductors reasonably close together. You don't want them sandwiched on top of each other like the GoHertz cable did years ago. When you sandwich 2 flat conductors on top of each other, yes, you get incredibly low inductance, but you also get incredibly high capacitance, and you don't want high capacitance within reason. You don't want nanofarads a foot of capacitance. If you're running long runs, it could potentially cause, weak amplifiers to oscillate, or it could cause frequency peaking on very wide bandwidth amplifiers. So capacitance, you don't usually have to worry about it if it's under a couple of 100 picofarads a foot. But if it gets really high because you're sandwiching conductors on top of each other, that could be a concern. And in those cases, when a cable company does that, they usually put a Zobel network, which is usually a resistor and a capacitor on the other end of the network next to where the speaker side is. And that helps alleviate some of those issues. But in this case, because they ran a bunch of solid conductors in the middle here and solid conductors here, there's a big distance here. There's basically, that looks, I don't know, maybe about little less than a half inch or so, maybe a quarter inch. That distance is what's causing this amount of inductance on this cable to have more inductance than standard 10 gauge that I measured. If you look at the 10 gauge Belden, those conductors are much closer spaced. Really makes a difference there. So the next thing I want to go over is capacitance. Now, this is the interesting thing. This is where this little battery pack comes in. Okay. So far, when I plugged the battery in and out, I measured it resistance. It didn't have any effect. I measured inductance. It didn't have any effect. But when we look at capacitance, here was what got interesting. So you look at the 10 gauge cable that has the lowest capacitance. The Kimber has the highest capacitance, again, because it has the lowest inductance. It's around 100 picofarads a foot. But here's what kind of surprised me. The Thunderbird cable actually had about middle of the road capacitance, but when you had no battery bias, the capacitance actually dropped. And I was thinking to myself that it doesn't make sense that the battery is making the capacitance go up, because if you think about when you bias a capacitor, I'm talking about a real capacitor, not a cable. When you bias a capacitor, it's used sometimes when you have a capacitor that has a very high dielectric constant. They put a DC voltage on it, usually to linearize the response of the dielectric, so it keeps the capacitance. Sometimes it minimizes the capacitance, it just stabilizes it, because a capacitor could change value based on temperature or bias voltage, because you could get bias currents in it. So there are cases where you DC bias a capacitor. It could also reduce distortions. There's all sorts of benefits to biasing a capacitor, but a cable is not like a capacitor. It doesn't have a lossy dielectric like a capacitor, not at the audio frequencies that we're talking about. I wrote a whole article about this, and I don't want to really dive into it too much here because it's very complex, but I'm going to show you the basics of what we did here. So one of Audioquest's claims is that their cable eliminates dielectric absorption. So I did this whole thing about dielectric absorption. And basically what I found was the dielectric constant, even of PVC, is in mega ohms at up to about a couple of hundred kilohertz. So that could never have a problem. You can never have dielectric absorption in a speaker cable. It's complete nonsense. And if you want to look at this article, I really suggest you go over it. I go through all the equations. I even have simulations. And then I even bring in some experts like Dr. Howard Johnson, who's one of the most prominent experts in skin effect and signal transmission. And he talks about breaking up basically transmission line theory and signal propagation into these 5 regions. So at the RC region is a very low frequencies like the audio range. And as you guys know, I always tell you, speaker cables, the most important metric in speaker cables is resistance. And then on interconnects, you have to worry about capacitance. Then when you want to worry about a little bit higher frequencies, it's the LC region. And then you can calculate the characteristic impedance of a cable by using the square root of L over C. And I'll show you that in a minute. Then when you get above audio frequencies, you worry about the skin effect region, as I was showing you. And then I'm talking hundreds of kilohertz, megahertz range. That's when you start worrying about the dielectric loss region. And then when you get into the gigahertz region, you get into the waveguide dispersion region. So this whole dielectric thing about biasing the dielectric for distortion, it's complete nonsense. It has no relevancy at audio frequencies, and especially with audio cables. And anybody that's trying to tell you otherwise just is going against the grain of science, provable science, stuff that's been around for hundreds of years that is well understood. Nothing I did here is misunderstood. This is all stuff that I picked up from my engineering training over the years. I've had PhD people teaching me these kind of things. And this is the kind of stuff that you have to know when you're doing board design, or you have to know when you're doing high-speed signal propagation, or you're doing any type of long-range distribution of signals that are small signals, and you're dealing with high frequencies, and you have to worry about transferring power without reflections and without distortions. This is all stuff that's well understood. I just want to be really clear about that, because I know people are going to say, well, how do you know, audio is so complex. Audio is a music signal. No, we know very well how to propagate signals down a piece of wire. This is not something that's misunderstood, or sorry to say it. And I'm not trying to bash anybody that believes in that stuff. I'm just trying to educate. And if you like having a cable that looks like this and it's heavy and it has a little battery pack on it, you know, more power to you. You know, if you want to spend $5 grand on speaker cables, I'm not here to tell you not to spend $5 grand on speaker cables. I'm just here to give you some truths, here to give you some science. So what I did next with this cable is I wanted to measure how it performed when plugged into an amplifier and into a loudspeaker, and I used my audio precision analyzer. Now, the amplifier, last time I did a test, I used the Denon integrated A110 amplifier, which is a great amplifier. But people are saying, well, you need to use higher end equipment. Okay, so I used a $6,000 Anthem STR amplifier. That's the amplifier that was used in these measurements. And I still use the Revel F328BE speakers, $16,000 speakers, $6,000 amplifier. I would venture to say most people will agree that's decent equipment, okay? So I want to show you first the frequency response. Now, understand one thing. I only had an 8-foot pair of Audioquest cables. So I ran an 8-foot pair of cable and I compared it to 10 gauge, 10-foot cable. I didn't want to cut my cable. So the 10-foot 10 gauge cable is at a disadvantage because it's 2 feet longer, it has a little more resistance than the Audioquest cable, but that's okay. I just want to make it clear that the 10 gauge cable was longer than the Audioquest cable. And you can see a very little difference here at low frequencies. We're talking 0.055 dB, 0.05. That's not something that's even detectable. But there it is. And this is only because the Audioquest has a little bit lower resistance because it's a shorter cable. Since coming in, you can see that the 10 gauge actually had less loss at higher frequencies. Now look at the scale here. I'm basically my vertical axis is about 2.5 dB. I had to really zoom in to see this. Now people are going to say, well, why didn't you measure the acoustical output of the speaker? You can't really do that. For these kind of minute measurements, you'll have too much variance in the microphone and the variance in the measurements in the acoustics of the room that would interfere with even seeing this type of stuff. This is why you have to look at the electrical response at the speaker load with the cable plugged into an amplifier. As you can see, there's very little difference in frequency response here between the 10 gauge and the Audioquest. And we saw this last time when I did the video on the 14 gauge versus the Kimber cable versus the 10 gauge. But here's what I want to show you that's interesting. This battery thing, this did not make sense to me that when the battery was turned on, that the capacitance went up on the cable. It should go down, as I told you, with capacitors when you bias a capacitor with DC voltage. I couldn't figure this out. I spent, you know, a couple hours at night just banging my head, looking through all my old books. And I'm like, this just does not make sense. But I had a hunch and I wanted to see if the battery was causing this problem or if there was something else going on. So let me show you what I did here. Okay, we are measuring parallel capacitance of the cable. We got the dielectric bias system engaged. And as you can see, the capacitance is showing you 566 picofarads for the entire cable. Now, when I disconnect the battery, you see the wires disconnected, and the capacitance has dropped to 506 picofarads. So now we're trying to figure out, is the battery really doing it or is there some other mechanism? So what I'm going to do now is I'm going to remove the battery. And this is a bit of a chore. It's hard to get this case open. There's a little tab you got to slide out. And you can see I've removed the battery here. 6 batteries, 12 volts each. Got to reconnect my cable. So the cable is now reconnected. The battery pack has been removed. And you can see it's 505, 506 picofarads. Same thing we got when we disconnected the cable before, the battery pack. Now I'm plugging the empty battery pack back in. And whoa, the capacitance went right back to 565 picofarads. So as you can see, with no battery in, just the battery connected to the holster and to the cable, the capacitance went up the same amount as when we had the batteries in. So the battery were essentially doing nothing. It's not the battery. What they did was when they connected this wire through their shield or whatever they have here that goes into the dielectric, it's acting like a parallel capacitance. It's adding capacitance to the cable. So just by, with no battery in it, just by connecting this in, not only does it add capacitance, but I suspect it's going to act like an antenna. So I wanted to measure some distortion to see what this battery pack does when it's plugged in versus when it's disconnected. I want to show you that now. I mean, you just can't make this kind of stuff up. In 1,000 years, I would never have dreamed somebody would basically put something on a cable that would make it measure worse. I don't get it. Maybe you guys get it. I don't know. Maybe you could leave some comments down below about that. So, okay, I want to first show you the baseline of 10 gauge cable. I measured the 10 gauge cable plugged into my Revel speaker from the Anthem STR amp. You could, and this is a very low signal. It's, you know, it's under a watt. I wanted to keep it really low to see the small signal noise. And you can see the 10 gauge doesn't have any distortion. There's a little bit stuff here that's coming in from, you know, maybe the amplifier, some switching distortion or whatever that's going on from a clock. I don't know. There's just some noise here. It's well below detectability. It's at 0.03% THD plus N. Now look what happens when I plug the Audioquest cable in. Boom. Wow. Now you see our noise floor went up here. It's doing some weird stuff over here. It really went up here. I don't think it's detectable because it's still at 0.02% here, but who knows, you know, who knows when you're cranking it up if it can amplify that even more. But look at these spikes. So whatever kind of noise was in the room next to the amp or whatever, it basically amplified that. You didn't get this with the 10 gauge. Look how clean the 10 gauge is. Bam! That's with the battery pack Audioquest. So now I want to see what happens when you unplug the battery pack. Now the green is unplugged. The purple is plugged in. So the green still has some noise pickup, but these big peaks here that are at 0.1% are gone or they're reduced. You see they're here. They're at 0.05% here. They're at 0.035% here. Still, compare that to the 10 gauge. So you can see that there's definitely noise pickup caused by the Audioquest cable that you don't have with the 10 gauge, whether the battery is in place or not. Now I did these, I had the battery placed on the amplifier side for these tests. I think Audioquest has a directional arrow on their cable. They recommend you have the battery on the speaker side. So I went and I reran that test. And I have the measurement here. So you can see it's not quite as bad, but you still have these dominant spikes here that are almost at 0.1% THD that I did not have with just regular 10 gauge. Now the level shifted a little bit because I changed the amplitude of the signal when I reran this test, but still these spikes are not present with the 10 gauge cable, or they're much lower. They're almost in the noise floor. Versus having it on the battery side, on the amplifier side, it's worse. It's basically showing you that it's acting as an antenna. So the question you guys need to ask yourself is, do you want to spend $5 grand on a pair of speaker cables that potentially can act as a noise induced to your system? It can act as an antenna. Do you want to have that kind of signal going into your speakers or into your amplifier? I'm not here to judge. If you prefer more distortion, there's people that prefer, you know, tube amps because they have higher order distortion. Are they right or are they wrong? I'm more or less here to talk about the accuracy of signal propagation. And my goal is to have a cable that is no cable at all, that has the least amount of losses, not a cable that acts as an antenna that induces noise into your system. The whole point of a high fidelity playback system is to reduce the noise floor, to reduce the distortions. Audioquest is not living up to their name. They basically said they have a noise mitigation system on their cable. That's not the case. It's doing the exact opposite. They claim they fixed skin effect. That's not the case. You saw the AC resistance go up. They claim that they linearized the dielectric. Again, that's not the case. We saw that it's not even an important factor when it comes to speaker cables. So I want to also go over the rest of their literature here before we close this video out. So they make a lot of claims, Audioquest. You know, they have this zero tech, no defined characteristic impedance. They're basically claiming they're eliminating the characteristic impedance of the cable. I don't even know what that means, to be honest with you. It just doesn't make sense to me. As I told you in the past, characteristic impedance doesn't matter when it comes to audio frequencies. Okay. But characteristic impedance is something that's very easy to calculate, even at audio frequencies. It's a very basic formula, as I was telling you about the LC region before, the different regions of signal propagation. Characteristic impedance of a cable, be it coax or twin feeder or speaker cable, it's basically a relationship between the inductance and capacitance. So it's the square root of L over C. Audioquest is claiming that their cable has zero characteristic impedance or minimal characteristic. I don't even know what that means. But in order to have a zero characteristic impedance, you'd have to have no inductance, right? You'd have to have a zero over a number, which would be zero. That's not the case. You can see right here, the Audioquest cable has 0.225 microhenries per foot of inductance. The battery has no effect on the inductance, no effect on the capacitance, other than the fact that when that connector is tied to the battery pack, it causes higher capacitance. So I calculated it. I basically took the Audioquest with the battery. I did the square root of L over C at 1 kilohertz. It's 56 ohms versus 60 ohms without the battery. What does that mean? That's irrelevant, because when you're dealing with a speaker and an amplifier has vanishingly low output impedance, and the speaker has a variable impedance because it's a reactive load. So if an 8 ohm speaker, it might swing up and down from 3.5, 4 ohms all the way up to 20 or 30 ohms. So there's really no way you could have a perfectly matched characteristic impedance between an amplifier and a speaker. And again, at audio frequencies, it doesn't matter. It's just another one of those myths that Audioquest is reporting on, that they have some technology that you can't measure that somehow gets rid of characteristic impedance. And we saw here that the 72-volt dielectric bias system, it doesn't do what they're saying. It's not trapping radio frequencies, as far as I can tell. In fact, it added noise. It was picking up noise. It was doing the exact opposite. So I could go over this with a fine-tooth comb, but that's not the point. The point is that this cable, let me grab it again. This cable does not live up to the marketing claims from my measurements. It's difficult to work with, in my opinion. The connector breaks pretty easily on it. As you can see here, just by sticking it in the amplifier, it broke off. I was shocked at that. It's very stiff. It adds a lot of weight, so you got to be really careful when you're connecting it to a speaker or an amplifier. And it's cost prohibitive. I mean, if your speakers are 10 or 15 feet away from the amplifier, this cable can run over $5,000, $6,000, $7,000. So the question I have for you guys is, do you think that the $5,000 investment in this cable will bring you some type of sonic nirvana over 10 gauge? That's 50 cents a foot. Or do you think that $5,000 could be better spent on acoustical treatments, maybe upgrading, adding a second subwoofer to your system, maybe getting better speakers, better amplifier, paying a consultant to optimize the room? So these are the kind of questions I have for you guys. I hope you understand that I am not bashing anyone that spends money on cables. I'm just trying to get you guys the actual science of it, because the science that's on that website is nonsense. And they're not the only ones in the industry that are doing that. A lot of these high-end cable companies sell you a story. You know, they sell you a cable that it's got a fancy name. It's the Anaconda, or it's some snake, or it's some tropical island. And they sell you pseudoscience wrapped around it. That's my biggest beef, is the pseudoscience. I don't care if they want to charge $10,000 for a speaker cable, if it's pretty or whatever. Just let's be honest. Give me some specs on the cable so I know at least it measures as good as 10 gauge Belden cable. That's 50 cents to $1 a foot. Give me some real specs, and don't give me the jargon. Don't give me nonsense. If you're going to give me some real information about the cable, give me the facts based on provable, repeatable engineering science. All these measurements I did today are very easily repeatable. In fact, Amir over at Audio Science Review, he did an Audioquest cable measurement. I think it was on an interconnect, and he saw the same thing. He saw noise increasing at the low frequencies. He couldn't explain it, but I think I found the reason why. I think in his case was the same. That battery pack, even without the batteries plugged in, was acting as an antenna, and it showed the higher pickup of noise in his very sensitive measurements. So I'm not the only one. I'm glad there's other people that are out there doing this, and we need more of this. So I encourage anybody that is an engineer out there that wants to talk the truth about signal propagation and audio cables, please, I could use your support, because I take a lot of heat over being one of the only few people that do this. And I take the time because I think it's an important topic. I think truth is a marketable commodity. And I think that's one advantage that we have over many of the YouTube influencers or many of the reviewers online, is they just don't have the measurement tools, or they don't have the knowledge to refute these claims. Because let's face it, these claims sound interesting. I mean, they tell a good story. And if I didn't have the technical background that I had, I would probably believe it too. But now you know better. So why don't you do me a favor? Tell me what cables you're using. Tell me if you fell victim to some BS marketing that you now realize was nonsense. And tell me if these educational videos are helpful to you to understand signal propagation. And we'll continue to, we'll continue to throw in cable articles and cable videos. I'll link down below that skin effect article and the dielectric absorption article. Those are very heavy reading articles, but they're necessary. They're necessary to defend the science behind signal propagation for audio, because it's not a mystery to anybody that's outside of consumer audio. If you're in pro audio, or if you're in any kind of discipline that involves signal transfer, this is no mystery. The only mystery is when you're dealing with consumer audio and you're dealing with the high end. So that's all I have to say about that. Please don't forget about our Patreon channel at patreon.com/audioholics. You get direct access to me if you want to ask questions or suggest video topics. Don't forget about our weekly educational seminars on acoustics with Anthony Gramani. Those are at 11 p.m. Eastern on Thursday nights. And all I could say is be kind. We're not trying to start an instigation of war here. We're just trying to give you the truth. And until next time, my friends, keep listening.